Before Newton did his work with gravity, there was actually a lot of studies that had been done on planetary motion, and there was a guy named Johannes Kepler who came up with 3 laws that describe planetary motion. His first law that he came up with was that planets move in ellipses, and the sun is at one focus. Planets move in ellipses with the sun at one focus. Now, quick refresher on an ellipse. An ellipse is oval-like. It's got 2 foci. And what we do to draw an ellipse is if we take a string and we loop it around both of those foci, and then the third point is where we place our pencil. So we have a string stretched taut between those. This point where I put my pencil, if I drag that around those 2 foci, it'll carve out an ellipse. And an ellipse has a curvature. It's not an oval that's flat on both sides and rounded on the ends. It's actually curved all the way around. So I did a poor job of drawing an ellipse there. But Kepler's first law says that the sun is at one foci and the planet orbits in this ellipse. There is no other body over here. There's not another thing at this foci. Okay, or this focus. So that's the first law. Second law says that equal areas sweep out equal time, or equal areas are swept out in equal times. So equal areas are swept in equal time. Now, what this means is as the planet is orbiting, say it goes from here to here, this area that it takes is going to have the same area as this area, as long as the time it takes to move from 1 to 2, this time, t, is equal to the amount of time it takes to move from here to here. Now what we can see from that is that the planet is moving faster when it's closer to the sun, and it's moving slower when it's farther from the sun. Kepler said this is what happens. He did not say why. The third law of Kepler's planetary motion is actually an equation. And Kepler's third law says that the square of the periods of 2 planets is equal to the ratio of the mean distances from the sun. So he knew it wasn't a circle, he knew it was an ellipse, but the mean distance, or the average distance from the sun to its orbit, which he called S, okay, the ratio of the periods squared is equal to the ratio of the cubes of those distances. These laws were written before Newton's law of universal gravitation, but once we had Newton's law of universal gravitation, it's able to explain these things. So why does a planet move faster when it's closer to the sun? Well, remember, the force that's causing it to go is the force due to gravity, which is equal to m1, which would be the mass of the planet, times m2, the mass of the sun, divided by the distance between them squared, times universal gravitational constant g. Well, the masses of the planets are not changing, but the radius is. If the radius gets small, this fraction gets big. And remember, this is equal to m1, mass of the planet, times its velocity squared over the radius. So if the radius is getting smaller, and the force is proportionate to the square of that, then the velocity has to increase. So bigger force means a greater velocity. Now, we take that and we combine that with another planet to actually derive the third law. So if we take Newton's law of universal gravitation and we say the force acting between two things is equal to their gravitational force, mass of the sun times the mass of planet 1 times universal gravitational constant g divided by the distance between them squared is equal to the mass of that planet, m1, times the centripetal acceleration, which we can write as 4 pi squared r over t squared. That means if we solve this thing for t over t and r, I suppose, we can say that the mass of the planet doesn't matter, and so I have the mass of the sun times g. I'm going to divide both sides by 4 pi squared, divided by 4 pi squared, equals, I'm going to multiply both sides by r squared, so I get r squared times r is r cubed over t squared. Okay, and so what that tells us is that the mass of the sun and g and 4 pi squared, those are constants for every planet orbiting the sun. That's equal to r1 and t1, r1 cubed over t1 squared, so the period of that planet divided by the mean distance from the sun, right? It's not a perfect circle, but we average that and we call it that mean distance s instead of r. Then we're looking at this notation. And so for a second planet, we would have exactly the same thing, except this would be r2 cubed over t2 squared. And we can multiply both sides by t2 squared and divide both sides by r2 squared, or r1, I guess, and we would get t2 squared over t1 squared equals r2 cubed over r1 cubed. That is Kepler's third law. And so we derived it from Newton's law of universal gravitation. So Newton's laws were actually able to describe or explain why Kepler's laws worked.